Hello everyone, welcome to JCE Connect. In previous lecture, we have started module number 4, that is impact of jet on a curved vanes. There we have discussed about impulse momentum principle and some of the basic concept which are being using for the analysis of hydrodynamic force. So in this particular lectures, I'll be taking some of the cases that is force exerted by a liquid jet on a stationary curved vane. So in this, as we know, we have to use the impulse momentum principle. Since the force is acting in a very short interval of time on the vane, and that force we need to calculate by using the impulse momentum equation. So what that equation says, that is a force in x direction is equal to the rate of change of momentum in the direction of jet. In whichever direction the jet is acting and also exerting a force, in that direction the momentum of the liquid get changes. So that is impulse momentum equation, that is rate of change of momentum in the direction of jet, that is given as mass flow rate into change in velocity in the direction of jet, which can also be written as mass flow rate. So as already we know that the mass flow rate can be written as rho q into bracket the final velocity minus initial velocity, you can write, or else you can write rho q into initial velocity minus final velocity. Okay, so that is mass flow rate into change in the velocity. Anyway, it gives you the change in velocity. So that is initial velocity minus final velocity on the basis of, so here on the basis of the type of curved vane or the plate and the direction of the jet striking the vane, the following three cases are considered. So here, what are those cases? The jet striking a symmetrical stationary curved vane at the center. Means if the jet is coming in this direction and hitting the curved vane at the center like this. So what is the force exerted by the jet? So the jet striking a symmetrical stationary curved vane at the center. When it hits at the center, then the water deflects in this direction as well as in this direction symmetrically. Okay, that is the first case. Second case, jet striking a symmetrical stationary curved vane tangentially at one of the tips. Means it's just moving in this direction and this is the curved vane like this, but hitting at tangentially like this, or if this is the curved vane, if the jet may strike in this way tangentially to the curved vane at one of the tip like this. So why it is calling as symmetrical? So the whatever the angle with jet enters into the curved vane, so it is entering with some angle, say this is theta. So with what angle it is entering, with the same angle it may get out, it exits. If you take angle here, this is also theta. So this is called symmetrical case. The jet striking a stationary curved vane tangentially at one of the tips. So this is acting tangentially. It is entering with angle theta and leaving also with an angle theta. Okay, so these all cases are fixed cases. This is also fixed one. Okay, the third case, jet striking unsymmetrical stationary curved vane when the jet striking tangential at one of the tips. Means this is the curved vane and it is a fixed one. How the jet is striking? It is striking tangentially at one of the tip. These are called as the tips or ends, tip of the vane or tip of the plate. Okay, so this is the edges. it is striking at one of the tip tangentially. When it is striking at one of the tangential, it is making an angle of theta here. So it is making an angle of theta with the horizontal. So it will be entering with some angle theta, and again it will be leaving like this. It will be leaving here. So when you draw horizontal here, so it will be leaving by some other angle, say pi. In previous case, so in this case, when the jet was striking at one of the tip, and it was entering with an angle of theta here, and it was leaving with same angle theta. See, it was entering with angle of theta here, and it was leaving with the same angle theta. It is called symmetrical case. But unsymmetrical case, what happens? It will enter with some angle into the vein, and it will leave with some other angle, say pi. So entry angle here is a theta, exit angle will be pi. This is unsymmetrical case. So these all cases are fixed case or a stationary case. When the veins are stationary and the jet will be striking the vein, what is the hydrodynamic force it exerts, that we need to calculate it. So this is a force exerted by a liquid jet on a stationary curved vein. So these are very, very important derivations. These derivations are very, very important. So for these all derivations, we use one concept, that is impulse momentum equation. So what impulse momentum says? The force which exerts, that will be equal to the rate of change of momentum in the direction of jet. Okay. So let us take the first case. So in the first case, so here I am considering the jet striking a symmetrical stationary curved vein at the center. So consider this one. So consider a jet of water. So here I'm taking this is the pipe. The water is flowing through this pipe, and a nozzle is fitted at the end of the pipe. A nozzle is a gradual reduction in cross-sectional area. This is called a nozzle. The purpose of fitting a nozzle is just to increase the kinetic energy of the liquid here. Okay. Then when the water comes out from the nozzle, it will come in the form of a circular rod or a non-circular rod with a high kinetic energy. Okay. Then it comes and hits the vein, and it is hitting at the center. That is our first case. We are considering jet striking a symmetrical stationary curved vein at the center. So we need to calculate what is the hydrodynamic force the jet is exerting on the vein. So consider a jet of water of diameter d moving with a velocity v. This is moving with a velocity v, this jet, and strikes symmetrical curved vein at the center. While repeating, consider a jet of water of diameter d. This is the diameter d, moving with a velocity v, strikes a symmetrical curved vein at the center. So this vein is placed symmetrically, means the jet is striking exactly at the center. Whatever the quantity of water is moving in this direction, the same will be moving in this direction also. So with whatever angle it is been deflecting after striking, with the same angle it is also deflecting here. So here it is marked angle of deflection. It is moving, or it is deflecting at an, after striking it is deflecting at an angle of theta here. Okay. So when it strikes at the center symmetrically, which is shown in the figure, then we have to also consider that there is no loss of energy due to impact. So this is the assumption we have to make after striking the jet. After striking the jet at the center, there is no loss of energy. So this surface of the curved vein, this is inner surface of the curved vein, we have to assume it is perfectly smooth. It's very, very smooth. There is no any loss over here. There is no frictional loss here. whatever velocity with which the jet is striking, this with the same velocity it is coming out, v. So here I consider the velocity of the jet as a v. With the velocity v, it is striking at the center. After striking, the water will glide over the surface like this, and it comes out with some angle. And whatever velocity with which the jet is striking, with the same velocity it is coming out. So there is no loss here. So that is the assumption we have to make. That is, we have to also consider that there is no loss of energy due to impact of jet. And one more assumption we have to make: the difference in elevation between the incoming and outgoing jets are neglected. So this is an incoming jet and this is the outgoing jet. Incoming and outgoing jet, the difference will be same here. There is no any difference in incoming and outgoing jets. That is also one assumption we have to make. Then the liquid jet, after striking the vein, gliding over the surface of the vein and comes out with the same velocity v. Okay, so it is coming with velocity v here and striking at the center, then the glides over the surface and it comes out with the velocity v. When it is coming comes out with the velocity v, which will be making an angle of theta here. Okay, so theta here. Then we have to resolve this velocity. One velocity we get as a v sin theta and another we get as a v cos theta here. Okay, now let us solve this one. Then to write here the velocity at the outlet of the plate, the velocity at the outlet of the plate, velocity at the outlet of the plate can be resolved into the following two components. The first component is component of velocity in the direction of jet. So here, if you take the first component, the component of v, in the direction of jet is this one. So this jet is coming with a velocity v and striking the vein, and it is going out of the vein with same velocity v, making an angle of theta. When you resolve this one, we get two components. One in the direction of jet, other one is perpendicular to the direction of jet. So when it is coming in the direction of jet, both are parallel here, but it is in opposite direction. Okay, this is in opposite direction. V is, so one v is going in this way. See, the v is going in this way and the component of this coming out like this. So it is v cos theta. I hope you understood this one. Okay, so the component of velocity in the direction of jet, which can be written as minus v cos theta. The minus sign, why the minus sign? It is coming in the opposite direction. Negative sign indicates that the velocity of the jet at the outlet is in the direction opposite to the jet of the fluid jet. See, this is the velocity v striking the vein at the center and coming out with a velocity v, making an angle theta. When you resolve this one, we get in the direction of jet but in opposite direction, v cos theta. Okay, second component, what we get? Component of velocity perpendicular to the jet, that is we get v sin theta in y direction. This one, we get two components at the outlet. So this is inlet and this is the outlet, here outlet. So one v sin theta and the other is a v cos theta. Then we also the mass flow rate of liquid striking the vein. Also mass flow rate, this already we discussed mass flow rate, how it can be expressed. So about this I explained in previous lecture. Mass flow rate of liquid liquid striking the vein means how much quantity of water is coming out of the nozzle here. How much quantity of water, that is called mass flow rate of water striking the vein. Mass flow rate. Okay, how much kg of water is coming out of the nozzle and striking the vein per second, meaning that is called mass flow rate. That mass flow rate can be given as rho A into V. As we know, as I explained this one, density is equal to mass by volume. So what is mass? Density into volume. But mass flow rate with respect to time is also divided by time. We get density into volume by time is what? Q. This Q can be written as A into V. This is called mass flow rate. This is called mass flow rate. Mass by time. Mass by time. Now let. So we want here hydrodynamic force in x direction. Let Fx and Fy, two forces we want in x direction as well as in y direction. So here this we take it as a Fx in x direction, Fx, and perpendicular to that we take it as a Fy. Let Fx and Fy be the force components exerted by the liquid jet on the plate in the direction and normal to the direction of jet. So let us take this Fx and Fy are the two forces. One is acting in the direction of jet, other one is acting in the direction normal to the jet. So the jet is coming in this direction and hitting the vein. So this exerts a force in x direction. Let us take that force as a x, that is Fx. Other one force is Fy, perpendicular to the vein. So these two forces we need to calculate here. Okay, so that way to consider Fx and Fy be the two force components exerted by the liquid jet on the plate in the direction of the jet, one force, and normal to the direction of jet will be another force. Okay, then next, then applying the impulse momentum equation. Now you apply impulse momentum equation. The force exerted by the jet in the direction of jet means we calculate Fx is, that is Fx, we want force in x direction exerting by the jet. So here the water is coming out of the nozzle with a velocity v, and this jet is having a diameter d, and it is striking the vein at the center. Then after striking the jet this water glides over the surface and leaves the vein with a velocity v, and while doing this it exerts a force in x direction as well as in y direction. So we have to calculate what is the force exerting by the jet on the vein in x direction. So to calculate that force we are using the impulse momentum equation. So what that impulse momentum equation says, Fx equal to rate of change of momentum, in the direction of jet, So in whichever direction the jet is acting, that direction the momentum to be considered. That Fx will be what? Mass flow rate into change in velocity, because we know momentum equal to mass into velocity. Since we are taking impulse momentum equation, so that is Fx equal to mass flow rate into change in velocity. Then mass flow rate, as we know how to write, rho into A into V. Change in velocity means initial velocity minus final velocity. Then this can be written as it is. You write initial velocity of the jet. How much is the initial velocity? V. So the jet is striking the vane at a velocity V initially. Then after striking, it leaves with a velocity V, but we want in x direction. So initial velocity will be V minus final velocity minus V cos theta. Why minus V cos theta? Look here in this figure. It is striking with a velocity V, that is the initial velocity, and it leaves with velocity V by making an angle of theta. But we want in x direction. The x direction is what? V cos theta, but acting in opposite direction. That is minus V cos theta. I hope you understood this one. Then finally what we get? Rho AV, we get V plus V cos theta. Finally we get rho A V square 1 plus cos theta. This is in x direction. This is equation. Then another one is second one. The force exerted by the jet, normal to the direction of jet, that is we want force Fy. So Fy, again the same formula, mass flow rate into change in velocity. The mass flow rate, what? Rho A into V, change in velocity, initial velocity minus final velocity. Then again rho AV. So what is the initial velocity with which the jet is striking? In y direction we want. So is there any velocity acting in y direction initially? No, there is no velocity acting in a y direction. So initial velocity is 0 minus. So what is the velocity in y direction? This is V sin theta. I hope you are understanding this one. So here there is no velocity acting in the y direction initially, but there is a velocity, that is the final velocity in y direction at the exit. So this is V sin theta minus V sin theta. So we get rho minus rho A V square sin theta. This is Fy. So the negative indicates the force is acting in negative y direction. Okay, finally means it will be acting downward. Finally the resultant, how the resultant can be given? The resultant will be what? Root of Fx square plus Fy square. This is the resultant force. And the direction, this is the magnitude, and the direction can be given as theta equal to tan inverse of Fy by Fx. Finally, so how it can be represented? So if the value of F you are getting one value, you get a positive, this is Fx, and another one is get Fy. The resultant of these two will be which one? This is F. Okay, this is angle theta. This is final representation of force. Okay, so this is the resultant of jet acting. Okay, I hope you understood this one. So please practice this derivation, and I hope you understood this one. And also remember, you have to apply the impulse momentum principle here. So first thing, you have to draw a figure neatly. that is a pipe and a nozzle, how it is acting, and which case is being given, what is a symmetrical case or a unsymmetrical case. Let us find out that, and then according to that you draw the figure, then you calculate the force exerting by the jet. Okay, so this is a symmetrical case, that is a jet striking at the center of the vein. So in next case we'll take, that is just striking at one of the tip of the vein. So next case, so next lecture we'll take this case. This is jet striking at one of the tip, and the jet vein is placed symmetrically. Okay, so this case we'll consider and we'll solve. Okay, in this particular lecture I'll be taking a second case, that is jet striking symmetrical curved vein tangential at one of the tips. That is a stationary case only. We had the first case, that is a jet striking symmetrical curved vein at the center. So we have solved in previous lecture, and we have got the equation also for that one. So in this particular lecture I'll be taking the jet striking symmetrical curved vein tangential at one of the tips. Okay, so in this case a curved vein is being considered, and that too stationary. This is fixed, and this curved vein is symmetrical about x-axis. So this is the x-axis and this is the y-axis. So this vein is fixed, symmetrical about the curved vein, and the jet is striking tangentially at one of the tip. So these are called as a tip of vein or tip of plate. These are called as a tips. Okay, so and here the water is flowing through a pipe. So this is water is flowing through a pipe. Again, for a pipe, a nozzle is been fitted at the end. This is a nozzle, just to increase the kinetic energy of the liquid. A nozzle is been fitted here, and when the liquid comes out from the nozzle, it will be coming with a high velocity jet. So this jet will be having a diameter d, jet of dia d. So this will be having a jet of dia d, which is striking at one of the tips tangentially. So after striking, the water will glide over the surface, then it will exit. Okay, but this is a symmetrical case. Again, as I said, symmetrical means this plate is kept symmetrical about the x-axis. Then whatever the angle it is making, the jet while entering, see whatever the angle it is making, so this is the direction of jet, and the jet is coming out of the nozzle with a velocity v. This velocity is v here, and if I draw it horizontal here, so it is making an angle of theta here. And when I resolve this velocity v into two components, this is the velocity v, and I'll resolve this one. So if this is one component, this is another component. So this component is v cos theta, and this component will be v sin theta. And after striking a jet, the jet will striking the vein at one of the tip tangentially, then the water starts gliding over the surface like this, then it exits like this. It exits with the same velocity v. Then here also it makes or it exits with some angle. That angle is theta here, and this component again becomes v cos theta, and this component will be v sin theta. And while entering, it making an angle of theta. If this is theta which is entering tangentially, if I draw a tangent like this, so this also angle theta. If this is theta, this is also theta, and this angle is 180 minus theta, This is called angle of deflection. Angle of deflection. Okay, so now in this case we have to calculate what is the force exerting by the jet on the vane in x direction as well as in y direction when the jet striking tangentially at one of the tip, keeping the vane, that is curved vane, symmetrical about the x-axis. So again symmetrical, whatever angle with which the jet is entering into the vane, with same angle it is exiting at outlet. Okay, here the same angle. So inlet angle as well as outlet angle will be same here. Okay, so in this case let us consider a jet of diameter d coming out of the nozzle with a velocity v, strikes symmetrically. It is striking symmetrical curved vane, that is a symmetrical curved vane at one of the tips. And here also you have to make an assumption that this inner surface of the vane is a very smooth, and the moment the jet enters into the curved vane, it will glide over the surface, then it exits without any energy loss, without any frictional loss. Okay, here, so with what velocity is entering, with the same velocity it is exiting. Okay, that is the assumption you have to make. Then let us take the v, that v represents the velocity of the jet and the theta represents the angle made by the jet with x-axis. That is angle made by the jet with x-axis at inlet as well as at outlet. So this theta is the angle made by the jet with horizontal at inlet as well as at outlet, and v is the velocity of the jet entering into the vane and exiting with the same velocity, because we have assumed this surface is very smooth. Okay, so after this, so let us apply impulse momentum equation as usual, you know. So for solving impact of jet problems, we have to use one theorem, that is impulse momentum theorem. That impulse momentum equation we have to use, and about this equation you all know. And this, why it is called as impulse momentum equation, that is the force which is acting in a very short interval of time by the jet on the vane, and because of that we have to use impulse momentum principle. So the force exerted by the jet in the direction of x, we want the force in the direction of jet, even though the jet is striking tangentially at one of the tip by making an angle of theta with horizontal, but we need to resolve, or we need to calculate the force in x direction and force in y direction. Finally we have to get the resultant of force, that is a resultant of force by the jet on the vane. Then here I am applying the impulse momentum equation. So we know the impulse momentum equation, that is fx. Why I am taking fx here? Because we want force in x direction here. The x direction force can be calculated, that is rate of change of momentum in the direction of jet. So since the force is applying in x direction, hence the momentum also we have to take in x direction. Okay, then what is the momentum? That is a mass into velocity. Since we are taking with respect to time, then it becomes a mass flow rate into change in velocity. So here the mass of the fluid coming out of the nozzle, whatever the mass of fluid coming out of the nozzle, that remains same. Only the change what we get here, velocity, the velocity get changes. So that velocity can be taken initial velocity minus final velocity. This mass flow rate is rho a v, that is rho is the density of the liquid, a is the area of the jet, and v is the velocity of the jet into initial velocity minus final velocity. Now I can write this one again. I can write rho av So I'll write what I'll write, v1x minus I'll take v2x. So what v1x represents? v1x represents initial velocity of jet in x direction. Initial velocity of jet in x direction. And what v2x represents? Final velocity of jet in x direction. Okay, so we want force in x direction. You have to take the velocity in x direction as well as that is initial velocity in x direction as well as final velocity in x direction. So now referring to figure, so you have to take what is v1x in this case. So here what is v1x? The v1x will be what? V cos theta. This one, because we want velocity in x direction. This is the velocity. This is the velocity. It is making an angle of theta. But when I resolve this velocity, this is the resultant velocity. When I resolve, I'll get a two components. One in the y direction, other one is the x direction. But I want velocity in x direction, that is v1x, v cos theta. Then what is v2x? v2x, again I'll get minus v cos theta. So because it is opposite to the direction of jet, so I'll get a minus v cos theta, that is final velocity. Then if I substitute here, what I get here? V cos theta minus of minus v cos theta. Then simplify this one, I'll get rho a v. This is v cos theta plus v cos theta. Take v out, rho a v square. That is, I'll get this one is 2. This v cos theta plus v cos theta becomes 2 cos theta. Then finally answer is 2 rho a v square cos theta. This is Fx, force exerting by the jet in x direction. This is the formula. Similarly in y direction, that is force exerted by the jet in y direction. So how I can write? Fy equal to, again, mass flow rate, mass by mass per second into initial velocity minus final velocity. Mass flow rate, that is mass by time. You can write it as a time, mass by time. That is written as rho a v. So initial velocity in y direction. So again referring to figure, so I can take v1y y direction, that is v sin theta, and v2y, I'll get v sin theta. So initial velocity in y direction, final velocity in y direction. So what you get here, I'll write here v1y minus v2y. So v1y, initial velocity in y direction, that is v sin theta, and v2y v sin theta. What I get? Rho a v sin theta minus v sin theta. So this 0, answer will be 0. This get cancels, you will get answer 0. So there is no force exerting by the jet on vane in y direction. Okay, so only the force is exerting in x direction. So finally the resultant can be written as root of fx square plus fy square. And what is the direction of the resultant? Tan inverse of fy by fx can be written. Okay, so this is the answer. I hope you understood this derivation. This is very important for the examination point of view. So here the jet is striking a symmetrical curved vein, but the vein is kept stationary and jet is striking tangentially at one of the tips. First you draw the vein, then allow the jet to enter into the vein tangentially. Okay, it is entering tangentially by making an angle of theta. So sometimes if theta is 0 means, suppose if theta is 0, so this is the vein. So when theta becomes 0, so it will enter like this tangentially only. It will enter tangentially. So this is also correct. That time V, this is V. Okay. So practice this derivation. I hope you understood this second case. Okay. In third case, what we take? So third case, we'll take again the curved vein, striking tangentially at one of the tip, but the vein is kept unsymmetrically. Means the jet will entering with some angle and it will exit with some other angle. That is unsymmetrical case. Means the vein is not symmetrical about the x-axis. It's not symmetrical about the x-axis. That is not mirror image of one another. If you draw a center line here, so this vein is not symmetrical about the x-axis. So how we can identify? The jet will enter with some angle and it will exit with some other angle. That is the third case. The jet striking unsymmetrical curved vein tangentially at one of the tip. So that we'll see in the next part of this lecture. So in this particular lecture, again I'll be taking the case 3, that is jet striking unsymmetrical stationary curved vein tangentially at one of the tips. So in previous lecture we have solved by taking the symmetrical stationary curved vein and the jet was striking tangentially at one of the tips. So in this particular lecture, a jet striking an unsymmetrical stationary curved vein and striking tangentially at one of the tips. So what is the hydrodynamic force? So here this is the figure. So this is a curved vein and it is a fixed one. It is a stationary curved vein. Means after striking the jet, the plate will not be moving in forward direction. That is, the velocity of the plate will be 0 here. There is no velocity of the plate here. The velocity of the plate will be 0, and here we made jet to strike the plate tangentially at one of the tips. These are called as tips of the vein or tips of the plate, and it is striking tangentially by making some angle with the horizontal, and the plate is kept unsymmetrically about x-axis. So this is x-axis. Okay, so for this case we need to calculate what is the hydrodynamic force in a similar way as that of previous cases. So we have to apply the impulse momentum principle for this also. Then we have to get fx and fy, then finally the resultant, and finally what is the efficiency of the jet. So in all the cases we need to calculate the efficiency of the jet. Okay, here this is the pipe. In this pipe the water is flowing again. So at the end of the pipe a nozzle is been fitted. A nozzle is a device where a gradual reduction in cross section area we get here. So the purpose of fitting the nozzle, that's to increase the kinetic energy of the water. When it comes out of the nozzle, the liquid will come in the form of a jet. So this jet will strike the blade or the vein at one of the tips. Then the blade will receive the hydrodynamic force. So since it is striking at one of the tip and entering tangentially into the vein, so inside the vein, so then it glides over the surface like this, then it glides over the surface like this, then it exits. Okay, so here assumptions, we are going to make an assumption that the inner surface of the vane is very smooth, hence there is no frictional loss here. So whatever velocity with which the jet is entering, so let us take the velocity of the jet as a v, and with the same velocity it will exiting at the outlet. Then if we draw a tangent like this, it is entering tangentially, this is a tangent to the vane like this, then this jet is entering with certain velocity by making an angle of theta. So if we take this one, so it is making an angle of theta here with horizontal, it is entering, then again it is exiting at the outlet, again it makes certain angle. These two angles are not equal, so this makes an angle here pi. In previous case, so we have seen both the angles were same, so that was the symmetrical case. This is unsymmetrical case, means it will enter with some angle and exit with some other angle. Entry angle here taken as a theta and exit angle is taken as pi, so both the angles are not same. So this is an unsymmetrical case. So let us consider a jet of diameter d and having a velocity v and striking at one of the tips of the vane and gliding over the surface, then it exits, and the surface of the vane is assumed as very smooth, hence there is no any loss here. Then when you resolve this velocity of the jet into two components, so one in x direction, other one is in y direction, so this component becomes v cos theta and this component is v sin theta. So since we want force in x direction as well as in y directions, so we have to take the velocity in x direction as well as in y direction. Similarly at outlet, so this is inlet, at inlet this is at inlet, so I taken this is at inlet, and at outlet of the vane. So again, if you resolve this velocity into two components, one in x direction, other one is in y directions, again we get here v cos pi and v sin pi. So I hope you understood this one. So again, as usual, after drawing this figure, then we have to apply the impulse momentum principle for getting the fx and fy. So since at inlet the velocity is making an angle of theta with horizontal, then this angle, when you draw the tangent to the vane, then this angle also theta, and this is pi, exit angle. Okay, this angle equal to this angle, this angle equal to this angle. Then this is a stationary vane, that is the velocity of the plate is 0 here. Let, I'll write here, let theta and pi be the angle, theta and pi be the angle made by tangent at inlet and outlet, inlet and outlet tip with x-axis respectively, and also v is the velocity of jet, and t is the diameter of jet, then a will be area of jet, that is pi by 4 d square we get. Then applying impulse momentum principle, then force in x direction, calculate force in x direction, that is fx equal to rate of change of momentum in x direction, because we want force in x direction. So whatever the force acting in x direction, in that direction momentum only we have to take. So then we get what we get here, mass flow rate into change in velocity. Okay, this is the equation we get. Next, further, Fx equal to mass flow rate, as you know, it can be written as rho av into initial velocity of jet minus final velocity of jet, but in x direction we have to take. Then Fx will be rho av, so initial velocity of jet in x direction. So this is initial velocity, that is v cos theta. Then this will be final velocity v cos pi. So what do we have to write here? Initial velocity v cos theta minus v cos pi. Then we get Fx equal to, take v out, rho a v square cos theta minus cos pi. This is the equation we get. Then similarly we have to calculate force in y direction. Similarly, force in y direction. Then Fy will be, again you have to apply the same formula, rate of change of momentum in y direction. Rate of change of momentum in y direction. So Fy will be mass flow rate into change in velocity. Again mass flow rate will be rho av. Change in velocity means initial velocity minus final velocity in y direction. Because we want force in y direction, we have to take the change in velocity in y direction. Again rho av, then initial velocity in y direction, so v sin theta, and final velocity in y direction v sin pi. That is v sin theta minus v sin pi. Then take v out, rho av square, sin theta minus sin pi. This is Fy. Then finally, what is the resultant? Root of Fx square plus root of, Fy square. Then what is the direction of resultant? Theta, that is direction, theta equal to tan inverse of Fy by Fx. This is the direction, and this is the resultant force. Then this is the directions. So suppose if you are getting Fx positive, you draw like this, positive, and again Fy also positive, you have to write like this. So this is Fx, this is Fy, then you have to draw a resultant like this. This is theta, direction, then this will be resultant. Suppose if you are getting Fx positive, then Fy negative, draw like this, negative y direction, and this is a positive x direction, then the resultant will become like this. Then theta will be, this is the final representation of the force. If both are positive, draw like this, resultant. If x positive, y negative, it will be like this, then you are getting like this. Okay, then suppose if you want to get suppose if they ask what is the efficiency of the jet. Suppose they are asking efficiency of the jet. So efficiency of the jet formula is input divided by output. So what is input here? Here input will be what? We are giving the kinetic energy input. That is the input. So output is work done. So kinetic energy of the jet will be the input and the output will be the work done. Okay. So how to get this one? Efficiency input. So here input energy, that is kinetic energy of jet per unit time. That is the kinetic energy. So we know kinetic energy is equal to half mv square. Per unit time is per unit time. Then again it becomes mass per unit time. Then we get this mass per unit time will what? Rho av into v square. We get rho a v cube. This is the kinetic energy. Then output is what? Output is what? Work done per second. Then how will you define work done? So when you say the work is being done, the work is said to be done when a force acts on a body and displaces a body in its own direction. Whenever a force acts on any body, if the body gets displaced, then we say the work is been done. Okay, so suppose if this is a body, if you are applying a force here, if the body get displaced certain distance, then what you say? The work is being done. If the body is not displacing even after applying the force, then the work done will be 0. You are applying a force on this body. If the body is not even displacing, not changing its position, then we say the work is not been done. Suppose when we say the work is been done, the work is said to be done when a force acts on a body and displaces the body in its own direction, then we say it is work is been done. Then the work done can be written as force into displacement. But per unit time, it is per second we want, because kinetic energy also we have taken a per second, then work done also we have to take the per unit time. Then we write time. And as we know, displacement by time is what? Velocity. So then the force into velocity becomes work done per second. F into V. Work done per second. Okay, this is the output. And input is what? This is the input. But in all the cases, whatever the cases we have taken, that is we have taken all stationary cases. See, so in these cases, if you take, we have taken the stationary curved vane. So let us calculate the efficiency in these cases. So what is happening here? The jet is coming out with a certain velocity, and here the input what we are giving is kinetic energy of the jet. So with this input, the water is entering into the surface of the vane. It will be gliding over the surface. Then the momentum of the fluid will taking place here. Here the momentum of the fluid takes. So because of the momentum of the fluid, the blade receives, that is the vane receives a force, and because of that force, if the blade get displaced, then we call it is work is been done. If the blade is not even displacing after applying the force, then we say the work is not been done. But in these cases, the blade is placed fixed, that is the plate is placed fixed. So there is no any movement, that is we have taken the velocity of the plate as 0, then the work done is 0 here. So in all fixed cases, whatever the cases we have been solved till now, so we have taken the first case as the jet striking at the center of the vane. We have taken the first case, you have seen the first case we have taken, the jet was striking at the center of the vane, where the vane has kept fixed, that is velocity of the vane is 0 and the jet velocity was v. And the second case we have taken when the vane is kept symmetrical about x-axis and the jet was striking tangentially. In that case also we have taken the vane is fixed, again the velocity of the vane is 0. In the third case also we have taken the unsymmetrical case, the jet was striking tangentially at one of the tip, but this also we have taken as a stationary vane, so velocity of the vane is 0. So in all the cases the work done is 0 because there is no any displacement of the vane. Okay, so if you take the hydraulic turbine and suppose this is the impeller of the turbine and this will be attached to the shaft, then on this impeller the blades are being placed like this. So the curved blades or the vanes or the plates you can call. So what the function of these blades will receive the kinetic energy of the water, so which is this energy is been feeding from the dam that penstocks are being provided, and through that penstock the water is been feeding into the turbine station, and this will be having a huge kinetic energy and it will striking the blades. So when it strike the blades, the water energy get converted into mechanical energy here. So my water energy get converted into mechanical energy just by rotating the impeller. So these will transfer, that blade will transfer energy from blade to the impeller, then impeller will get transfer energy to the shaft, then the shaft will transfer to the generators. So this goes on. So while doing this, suppose these blades are fixed, these are not moving, these are fixed. So whatever the energy you are applying, whatever the jet striking the blade, if the blade is not displacing, then there is no generation of power here because the blades will not be moving. Okay, these are fixed. So in this case we take the work done is 0. Okay, so when we say the work is been, when a force is acting on a body, on this body means this blade, when the blade get displaces, it displaces, then again next blade will come and stand before the jet, again that also get displaces, again the third blade will come and stand before the jet, then that also displaces, then it continues, and hence the impeller will get rotates, and impeller is coupled with the what? Shaft, and shaft is intercoupled with generator, hence the production of electricity. So then we say the work is being done, that is the output of the jet. So here input is the kinetic energy of the water and the output is work done. So in all these three cases, whatever the cases we have solved, three cases, the jet striking at the center of the vane and the jet striking at one of the tips, and the vane was kept symmetrical, then the jet striking at one of the tips when the vane was unsymmetrical. These all cases the we have considered stationary case, hence the work done will be 0. Hence the efficiency, if you want to calculate efficiency in these cases, as I told, efficiency of the jet, input by output. Input is kinetic energy per unit time, so we have taken, then the output is what? Force into velocity. So we have an input, then the output is force into velocity, but in all the cases what is the velocity of the plate we have taken? 0. Hence work done per second, that is output, will be 0. Hence efficiency of the jet in all the cases will be what? 0. There is no efficiency. Hence these all cases are not practically feasible. All cases, that is these all three cases are not practically feasible. These are to be studied only theoretically, since it is giving efficiency 0. The work done is 0 here. So these are only theoretical cases and these are not feasible for practically. Hence the next cases we have to take when the jet is striking the vane is also moving, that is moving cases we need to take the next. So next lecture. So I'll be taking the moving of veins. So jet striking the moving veins. Okay. So in that cases, the means next cases we have to take the same cases, jet striking at the center, but the plate will also moving. So this is a velocity. Okay. So it is striking the veins, then the plate is also moving. What is the efficiency it generates? Okay. So those cases we'll take in the next part of this lectures. So I hope you understood these all three cases, that is stationary cases. Remember, if in exam if they asked for stationary case calculate efficiency also, you calculate first the kinetic energy of the jet, that is the input what you are giving at the inlet of the plate. This is the kinetic energy, that is the input is kinetic energy per unit time. So this is the equation. Output is the work done, then work done per second, force into displacement per unit time, then the force into velocity we get. This velocity is velocity of the vane. Since in these all three cases the velocity of the vane is 0, hence the work done is 0, hence the efficiency will be 0. Okay, I hope you understood this. So please practice these problems and try to derive the equations once again. Thank you.